So in discussing nebular collapse, we'd said that the Jeans criterion was the mathematical analysis that showed you had the special conditions necessary for a nebula to collapse under its own mass. You have to have the temperature, the density, and the mass all just right in order for this to collapse. So that gives you the Jeans criterion. Well, we'd ended the last little mini lecture with this picture right here, and these are called Bok Globules. They're named after Bart Bok. Bart Bok, an American astronomer who studied little small cool nebulae. And so little globules, and they were in regions that were often places where it was believed that stars were forming. And so where there's a lot of interstar medium. So what happens is you have a lot of interstar medium, and it just kind of clumps up a little bit, and when it starts clumping up and gets cool, then gravity starts pulling these little cool blobs closer together to one another. So all the gas gets pulled together in these little blobs, and your typical Bok globule is somewhere around 100 solar masses, and they're very, very cool, about 10 Kelvin. Remember, that's 10 degrees above absolute zero, 10 degrees Celsius above absolute zero. And they're actually fairly large compared to the solar system. They're several light years across. And this cloud of gas is pulling itself together. It's cool, it's compact, and has quite a lot of mass in there, so it's exceeding the Jeans criterion. And so as it starts to exceed the Jeans criterion, you start to form things. The Orion area here in space is actually a region where there's lots of stars that are forming. And the Orion Nebula is, in fact, a region in here where stars are in the process of forming. And it's glowing because some of the recent stars that formed are causing the gas to glow. So the inner parts of the globules start collapsing. And then as they heat up, they start to fragment. So your globule clumps up into several little smaller globules. And that's an important point, because it means that typically you don't get just one star that forms, you get a little clump of stars that form. And but not all of the gas in the globule gets in there, so some of the gas that doesn't get into those smaller globules dissipates back into the interstar medium. Okay, if you look in the center of each globule, all this gas is coming together and squeezing in the middle. When you squeeze gas, it gets kind of warm. And so what's happening is right in the middle of the globule, the gas is kind of getting squeezed together and getting kind of warm in there. And where it's getting kind of warm, it's glowing a little bit in the infrared. Well, that ball of gas in the middle is what will eventually become a star. It's not a star yet, so we don't call it a star. What we do is we call it a protostar. So that's the term we use for something that's going to be a star. The outer parts of the globule are still there, and they're sometimes called a cocoon nebula because they're shielding the view of the star being born on the inside. The gas transforming itself from an interstar medium into a star. And so the cocoon nebula is shielding our view. What's happening is that gas is spiraling in. Okay, now it doesn't go straight in because any little slight distortion makes it off to the side. And then in physics, we have conservation of angular momentum, stuff going around. So as it comes in, it's going to conserve momentum and go faster and faster and faster. So this falling inwards, the term we use for that is accretion. And as it spirals inwards, centrifugal force causes it to flatten out into a disk, what we call an accretion disk, as it spirals into the protostar. The protostar is getting more and more compact. As it gets more and more mass, gravity squeezes it smaller and smaller. It gets hotter and hotter. It starts glowing now, probably kind of a dull red color. Glowing ball of gas. It's still pretty big. It's big as our solar system, but it's glowing. Okay, warm gas and shrinking and getting hotter and hotter and hotter, and stuff spiraling into it. And so angular momentum is conserved. You have an accretion disk. But the problem is that this idea of how stars form was originated back a very long time ago. Actually, the idea of how stars form like this started back a couple hundred years ago. And more recently, the mathematics has shown that, oh, wait, it's a little bit more complicated than that, because it turns out that the accretion disk gets to going so fast, it causes the protostar to go so fast that it would shred itself. It would tear itself apart if it got more than about 0.05 solar masses. So that means you can only get up to about 5% the mass of the sun. And if it gets above 5% the mass of the sun, then it shreds itself. Well, there's a lot of stars bigger than 5% the mass of the sun. So obviously something else has to be happening right here. We see this is the process because we look in the Orion Nebula and we can actually see these little disks of stuff swirling together around protostars. So we know this is what's happening. Well, it was later in the 20th century that they began to figure out the mathematics of what was really going on. And they said, well, wait a minute. All the stuff spiraling in is going to be getting hot. When it gets hot, it's going to knock electrons loose. When the electrons get knocked loose, then all this stuff going around in a circle like this is going to be electrically charged going around the circle. That means it's going to be making a magnetic field. Okay. That magnetic field is going to then direct other stuff. Okay, and so as the other stuff spirals in, it's going to spiral out the magnetic field. Okay, and so only some of the stuff actually gets running into the protostar, and the rest of it spirals out the magnetic field. And so your accretion process has these two jets that are flowing out in both directions. So we call them bipolar jets. And turns out any kind of accretion, not just with protostars, but even with black holes, have these jets that are spewing out. So everything is really messy eater. So you start with this big cloud of gas, okay, got hundreds of solar masses. It clumps up into about a dozen things that have a few solar masses, and each of those gives you a one or two stars, you know, that have mostly less than a solar mass. And so what happens to all this missing mass? Well, it goes spewing back into the interstellar medium, giving you the chance to make more stars later. So these bipolar jets, and so the accretion disk swirls around and it traps a lot of the stuff which goes spiraling out in these bipolar jets, and that carries a lot of the angular momentum that allows the protostar to rotate slower so it doesn't tear itself apart. Doing this allows you to now build a protostar, and theoretically it can be up to hundreds of solar masses. It really, you know, it's going to be, but it can be enormous. So this allows you to actually build stars now. Well, we actually see these jets. Turns out Hubble telescope looking in here, you can't see what's happening in here because what's happening in here is shielded by seeing all that accretion edge on. So we're shielded by the accretion disk, but these jets are spewing out in either direction from where the protostar is in the middle right there. And here, there's a protostar in here that we can see in infrared light, and these jets spewing out. Now, the interesting thing about these jets, right at the end of the jets here, right at the end of the jets, where it looks bright right here, that's where the jets are running into the leftover of the Cocoon Nebula and the leftover of all the other interstellar medium that's out there, and you're compressing it and making it glow. So those glowing patches were originally discovered by George Herbig and Guillermo Haro, and so They were so Guillermo Haro, Mexican astrophysicist, and so what they did was they discovered that these bright spots out there in space near where stars are forming, and so we call them Herbig Haro objects. They were later determined to be the shock fronts, or where these jets are slamming into the rest of the interstellar medium. So they're leftovers. So this is actually what they look like. Okay, so this is what they look like, and you see this is called Herbig Haro 1 and Herbig Haro 2, and right here in the middle somewhere where you don't see anything is the Cocoon Nebula blocking our view of the protostar and the jets they're spewing out. It's where the jets run into the outer stuff that glows, and that gives you the Herbig Haro objects. And so here's more pictures of Herbig Haro objects. This is actually a combination of visual image, which is the pink colors out here, and those squiggly lines are radio intensity maps from the Very Large Array. And so it shows you where the jets are and then where the visible